In a prior screencast, we discussed the stresses that developed in a tensile sample that was clamped in a machine and pulled apart. And we considered the forces acting on a hypothetical face if we cut the sample in two at various angles. So if you look straight on, we cut it at 0 at 45 degrees and 75 degrees and so on. In this analysis, we used a coordinate system that was rotated to the angle of the cut, and we call that angle theta. So we developed new axes. We call them x prime and y prime with an angle theta from the horizontal and the vertical. And we graphed the stresses acting at the hypothetical face as a function of theta, with theta running from 0 degrees to 90 degrees. And what we found was that the normal stress in the y prime direction was greatest when theta was equal to 0 degrees, and eventually went to 0 as theta approached 90 degrees. And what we also found was that the shear stress was equal to 0 when theta was equal to 0. It reached a peak when theta equaled 45 degrees right here, and then it went back to 0 as theta approached 90 degrees. The reason it went back to 0 was because of the large surface area that appeared in the denominator. So in this screencast, we'll investigate this effect a little bit further using differential elements to describe the state of stress within the sample. To do this, let's look at our tensile sample again, and we're going to cut the sample at even more angles. And in all cases, this is a whole piece, but I'm just making hypothetical cuts shown in red. So here are the angles. With the cut going straight across, we have theta equal to 0 degrees. Here's an example of theta equal 30 degrees, 60 degrees, 75 degrees, 105 degrees, 120 degrees, 150 degrees, and finally all the way back around to 180 degrees. Note the similarities between 0 degrees and 180 degrees. The two parts look identical, and that'll be important later on. Let's examine a few of the cuts in detail, the first one being at 0 degrees, the second one at 30 degrees, and the third one at 75 degrees. To do this, let's introduce what's known as a differential element, and I'm showing it as a square here. And the element can rotate. We'll start with x and y axes, x-axis being horizontal and the y being vertical, and the element can rotate, and here I'll rotate it, for example, to 30 degrees, where we've got our x-axis rotated to the upper left, or to the upper right, and the y prime axis rotated to the upper left. So there's at 30 degrees. Here's our cut at 75 degrees. And finally, we can continue going until theta eventually hits 180 degrees, and we're left with the original differential element. So we've got the square in the exact same orientation we had before, except the x prime axis now acts to the left, and the y prime axis acts downward, opposing the y axis. Here are the three differential elements again. It's theta equals 0, 30, and 75 degrees. You'll see these differential elements drawn as large squares, but in reality they're infinitesimally small. What that means is, let's take the differential element at theta equals 0 degrees, and I'm going to put it right on the gray material here in the lower half of our hypothetical cut. And I'm going to continue zooming in on this so we can really show what's going on. So this element, it's smaller than this, it's smaller than this, it's infinitely small as you can possibly imagine. So we'll just continue on, we'll just make it infinitesimally small. And I'll take that element and I'll draw it a little red dot there so we can see it as we zoom back out to the original view. We see a little red dot right there. So we're trying to identify the state of stress at that point of the material. And if I delete the dot and the arrow, you can see more clearly just how small these elements are. But we're going to zoom in on them so that we can actually draw the state of stress for all of these elements. Before I do it, just to be clear, here's the element at 30 degrees. All of these elements I'm drawing right in the gray, right below the cut. Alternatively, I could draw it right above the cut and we would come up with the exact same state of stress if we were right in the vicinity of it. But for the sake of this screencast, we'll just draw them right here in the gray region. So I'll make these three elements infinitesimally small just to demonstrate. So let's start with theta equals 0. Here we've got our tensile, our specimen that's being pulled apart by some force F. And we need to calculate the normal stress acting on this differential element. And in that case, we would call it sigma y, and that would be equal to F divided by the cross-sectional area of this cut right here. And I'm going to use red to denote normal stresses acting in the y or the y prime direction. So we've got sigma y here acting vertically. And I'm calling it sigma y. I'm not calling it sigma y prime simply because theta is 0 and we're still acting at the original coordinate axes. Sigma x, there's no normal stress acting left or right. The sample it's not trying to be pulled apart in this direction, for example. So sigma x, we would say, is equal to 0 for this initial state of stress. And there's also no shear stress in this orientation. In other words, the sample is not trying to slide to the left, for example, at the top, and to the right at the bottom of it. There's no stress acting in that direction. So we have sigma x is equal to 0, and tau yx is also equal to 0. So let's consider another extreme here, at theta equal to 75 degrees. This differential element here is sigma x prime. And sigma x prime, it's being stretched in that direction, so it's some positive value. We've got a blue arrow stretching the differential element that way, and a blue arrow stretching the differential element in this direction. Sigma y prime, it is present, but it's relatively small. At this angle, there's very little stress trying to pull the differential element apart in this y prime direction, but we'll still include it here. The other stress is a shear stress. And it'll become evident here in a second why it arises, but we're going to draw this, we'll call this tau y prime x prime. And what that means is that we're on a face that's normal to the y prime axis, and it's acting in a direction in the positive x prime axis. So I've got tau y prime x prime. The reason that stress arises is because as we pull the sample apart, this hypothetical cut would have a tendency, if there was no stress present in that direction, this sample would have a tendency to shift to the lower left at the bottom and to the upper right at the top of it and continue moving this way. So you might think of it as the shear stress is being supported by a hypothetical glue perhaps, and that glue prevents the crack from, or our hypothetical cut from sliding in that direction. And if we zoom in on our differential element here at 75 degrees, we would look at it, and at the top of it, this material is trying to move, the gray material is trying to move to the lower left, and the white material is trying to move to the upper right. So if we look at this, there'll be a shear stress acting on the upper left face in this direction, and the material below our differential element is trying to drag it down to the lower left. I could place another differential element just on the top of it, and here we see, in this case, the gray is trying to pull to the lower left on that differential element, and the white material to the upper left of it is trying to pull it to the upper right. So let's zoom back out. We'll draw these stresses on our differential element in a large scale. So here we've got tau y prime x prime acting in that direction. And I've also got the same stress acting to the lower left on the right-hand side. So here also is tau y prime x prime. And if these were the only stresses we had, it would suggest that our differential element is rotating clockwise because we have a net coupled moment between the two stresses. To balance that, of course, the material isn't rotating, but the material just on this face of it will act to the upper left, and the material on this face will act to the lower right. And we'll call this face is normal to the x prime axis, so we'll say this is tau x prime, and it's acting in the positive y prime direction. We'll call it x prime y prime. And the same notation will be true for this arrow down here. It's acting in the negative x prime direction and the negative y prime direction. We call this tau x prime y prime. And because the element doesn't rotate, the net moment has to be 0. And what we find is that tau x prime y prime has to equal tau y prime x prime. So oftentimes you'll just see this stress being reported, and it's implicit that the two stresses must be equivalent. See, we've come back to the original element, so I've got tau x prime y prime, and I'll draw the rest of them on here. So finally, let's consider what the state of stress looks like at various angles. We'll start out at 0 degrees. And I've drawn a horizontal blue line just for a reference. We'll go to 30 degrees, and this is 60 degrees, 75 degrees. And I've drawn a horizontal blue line just for reference. We'll start out with this angle is at 30 degrees. This angle is 45 degrees. Here we've got an angle at 60 degrees. I've also drawn one at 75 degrees. And this angle, it's hypothetical in nature, but we're going to use a right angle, and we'll call it 90 degrees. And I recognize it splits the part in two, but we're just going to orient the element 90 degrees from the horizontal. And then this one, it's now a larger angle. This is 105 degrees. And this opens up to 120 degrees. We've got 135 and 150 degrees. And finally, we'll come all the way around, and this is 180 degrees. And like we saw before, the part at 0 degrees and 180 degrees look identical. Here's my differential element for 120 degrees. And if I superimpose coordinate axes, I've got my x-axis horizontal, my y-axis vertically, and the axes are rotated by 120 degrees. So my positive y prime axis should actually be down here, and now so I've got my x prime axis here. My y prime axis also rotated counterclockwise 120 degrees. So here's my x prime and y prime axis. So remember that in all of these cases we've got our differential elements are infinitesimally small. So I'm just going to draw the box down here again just to emphasize that we're dealing with the gray material right before the cut. So here's what our stress element, our differential element, looks like at various angles. We start out at theta equals 0. All of the stress is normal stress acting in the y direction, or sigma y. And as I rotate it to sigma equal, or theta equal 30 degrees, what we find is the development of a little bit of a shear stress, the development also of normal stresses in the x prime axis. And as I continue to 45 degrees, for this particular sample, we find that sigma x prime, sigma y prime, and tau x prime, y prime are all identical. And I continue rotating to 60 degrees. Here's 75 degrees, and we see that sigma x prime now is acting in the vertical direction, and it's quite large. And as I continue to 90 degrees, what I find is that it's identical to theta equals 0, except now we've got sigma x prime acting vertically. And finally, we'll continue rotating 105 degrees. Here's 120 degrees, 135 degrees, and so on. And finally, we come all the way back around to 180 degrees, and the state of stress is identical to theta equals 0 degrees. And finally, here are some of those states of stresses overlaid over some particular angles of theta. Theta equals 0, we've got sigma y only. Theta equals 90 degrees, we've got sigma x prime only. And at theta equals 180 degrees, we've got sigma y prime only. And theta equals 0 and theta equals 180 degrees are identical.